All right, so when I made the video, I did not go over this little guy right here with the base of E. Has anyone ever seen that base of E before? This is, yeah, it's on the calculator. It's right above the LN button, right there. See the little E? Everyone see that? That is Euler's number. That's right, that sounds like an O. Why would I call that Euler's number? Well, here's why you would call it Euler's number. It's Euler's number. Euler's number. Did you hear that? Euler's number. Clearly not an American name. Euler's number. Euler. 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 Not Euler. No, no. Don't say it like an American. No, no. No, no. Euler. Euler. I'm not sure. All right. Sounds like Euler. Right. E, there's another place where it shows up, and I'll show you. You can also see it above the divide button. Everyone see it right here? So if you want to do just an E all by itself, hit second divide. There's just an E. So everyone go ahead and do second divide and just press enter. So E is approximately 2.718. But most of the time we have E with an exponent. So e to the first, e to the second, e to the third, e to the fourth, e to the x. Yes. Euler. It's his whole number. Yeah, someday there's going to be Katie's number. That's me. I'm Katie. Yeah, but maybe Rice won't be my last name forever. No, I'm just saying that maybe I'll get married eventually, you know? I'm just saying that maybe in my future I won't always just have cats and plants. That maybe there will be a Mr. Rice someday.
Oh, you didn't take your day? Okay.
I don't know. All right, let's move on. So the number is approximately 2.718. That's important. Write it down. Are you writing it down? Okay. So the information is the same for Euler, for Euler's number. So we're going to write, we start here with the horizontal asymptote is y equals 0. We still have the point 0, 1. We still have 1 and then the base, which is b. In this case, the number is going to be e, which is approximately 2.718. So when we graph this, we're going to have that horizontal asymptote at 0. And we're going to have 0, 1. And then we're going to have 1, 2.718 right there. Do you guys see how I did such a good job graphing 2.718? Looks very realistic. So when I connect these points, I make sure that my 2 points that I connect them and then they approach the asymptote, because I know that's what they do over here. They get closer to the asymptote. That's how asymptotes work. And then over here it looks like an exponential function and it goes whoop. Complete with the sound effect. It goes whoop. It's not whoosh. No, it's whoop. All right. Beautiful. All right. Now, so it's the same thing over here. You can see the transformations as over here. So I'm going to write ditto. Okay, glad we filled that out. I wrote this, ditto. Same. Yes, same. It says this stuff, yes. Yes, also. Yes, Jack.
Why is the point 2.718?
Is Euler's number. Well, Google it, look it up. Why is pi 3.14? I don't know. Because somebody decided it. Because Euler was a person who has a special number. Don't ask me about math history. I am not a history teacher. I am a math teacher. Okay? Don't ask me things about which I don't know. Okay? Okay? And Euler helps you find Euler stuff. Let's move on. All right? Okay, let's turn to the next page. All right, so now that we have learned the things which we know and don't know, I'm glad we've clarified that. Are we good with domain and range? Those make sense? Increasing and decreasing. We good? Those are pretty simple for these. All right, x and y intercept. Ooh, let's do the x and y intercept. Okay, so example 4. Let's grab our calculators. I'm going to hear everybody clicking because everybody's following along. So y equals, I'm going to clear this. So you're going to type the little negative. And then to get the e on your screen, you're probably going to use this one over here because we have e to the exponent. So see the ln button? So you're going to hit second and then hit the ln button. So second ln, there you go, pops that little e on the screen. And then we got x plus 5. Annika, if you're using your old school calculator, you're going to put the x plus 5 in parentheses. All right. Plus 1. Oops, make sure you get the plus 1 down there. There we go, plus 1. All right. What does what mean? This is the base of the exponent is 2.7. That you move left 5 and up 1 and reflect over x. Okay, so we're going to go ahead and hit graph. We want to make sure that our graph matches this graph, which it does. Okay, so I'm going to look for my x-intercept first. Do you guys want to do the scroll method, or do you want to do the left bound, right bound, and pick numbers method? Left bound, right bound, pick numbers. So second trace option number 2, I'm going to write that on my notes just in case I forgot. So I'm going to do second trace option number 2. Second trace option number 2. I can see that the x-intercept is somewhere between -8 and 0. So I'm just going to type -8 for left bound and 0 for my right bound. It's somewhere between -8 and 0. Okay, so that works. Everyone good with finding their x-intercept? Yes? Okay, so my x-intercept is -5. And then how do we find the y-intercept? Okay, second trace number 1. Number 1, x equals 0. And we get, big negative. Okay, so we got 0, -147.413. Okay. Remember, we also have the James method, which was just to hit the trace button and then type 0, which is faster, but I cannot undo my routine, which is second trace, number 1, 0. That is my routine. So that is how I shall teach. All right, we comfortable? We can type in E on our calculator. We can do a plain E. We can do an E to an exponent. We are comfortable typing in Euler's number, even though we don't know why he gets a special number. Pythagoras doesn't have a Pythagorean number. He has a whole formula, though. Yeah. Who else doesn't have their own number? So many people. Yes? Fine, let's look it up. All right. The number E. Story time. The number E is an important mathematical constant, approximately equal to 2.718. Hold on. It is called the natural number or Euler's number. Let's see. There are different definitions for the number e. Most of them involve calculus. One is that the limit of e, one is that e is the limit of the sequence. This is when we learn in calculus. Whose general term is 1 plus 1 over n to the n. The other is that e is the unique number to the area under the curve. So it's the area under the curve of 1 over x from x equals 1 to 1 over e. So you guys were kind of looking to, because you said pi is, pi kind of relates to a circle. So the answer for e is that if you were to take that rational function 1 over x, let me graph it real quick. 1 over x. If we were to graph 1 over x and go from x equals 1 to x equals e, if we were to shade right, in here, this part right here, that area would be e. There's a lot of different, just like there's a lot of different things about pi, there's a lot of different things about e. This is the one thing, I think Court brought this up maybe, is that Euler's identity states e to the I pi plus 1 equals 0, which is supposed to be like one of the most amazing equations in mathematics, because it's like, what in the world? So if you type in your calculator, we'll see if the calculators can handle it. E to the I pi plus 1, let's see if our calculators could do that. So e, the I button is above your decimal point. E to the imaginary pi plus 1 is 0. Pi is above the up arrow for your exponent. That is supposed to be one of the most amazing equations in mathematics. Like, people get that tattooed on their body. Yours didn't like it? Your calculator said, no thank you. Okay, are we satisfied that E is sufficiently important?
Yeah,
I guess. Alright. Okay, let's move on. Let's move on to our other questions. Did we feel okay about the end behavior? We could see how one side would be the horizontal asymptote and the other side could be positive infinity going up or negative infinity going down. Did we see the end behavior questions and we understood those? Yes? We were okay with that? Okay. So let's move on to example 5 and 6. This is where I need us to graph these using those little 3 important pieces of information. So this is the part, like, normally we would say, okay, for quadratics, we had x is -2 to +2, and then we would have the points 4, 1, 0, 1, 4, or for absolute value, we had specific points. For square roots, we had specific points. So the ones that we're going to do for this, we're going to have the horizontal asymptote, y equals 0, and we're going to use the point 0, 1. And we're going to use the point 1 base. And then we're going to take those points and we're going to do the transformations on those points so that we can graph each of these functions by hand. Okay, so we are not going to graph these in a calculator. We're going to graph them by hand. All right, so when you look at example 5, what is the base of the exponent? The base of the exponent is 3. So you can always tell what the base is because it's the thing that has an exponent. So if it has a base of 3, that means that the 3 is not a stretch. It's not a vertical stretch. That is not a transformation. That's the parent graph. It means that the parent graph for this problem is y equals 3 to the x. And y equals 3 to the x had different transformations happen to it. Okay? So the 3 is not a transformation. The 3 is not a transformation, okay? So outside of the 3, what are the other transformations? What are the other things happening to the equation that you can see? Okay, reflect over x, left 2. So we saw reflect over x, we saw left 2, and then what else did we see? Down 1. Okay, so I'm going to start off with this. I'm going to say, okay, first off, I have my horizontal asymptote at y equals 0. I have 0, 1, and we said our base is 3. So we're going to start off with a base of 3. So the first thing you always do is you take the b out and you replace it with the base that you had from your parent function. Okay? So of these transformations, which one has to happen first? Reflect over x. And which coordinate does that impact? Is it the x coordinate or the y coordinate? The y coordinate. So it takes a point that's up and it flips it down. It takes a point that's down and it flips it up. So it's going to take the y coordinate and it's going to make it negative. We're multiplying it by -1. So the horizontal asymptote is going to stay 0. Negative times a 0 is still a 0. And then the point 0, the point 0, 1 is going to become 0, -1. And then the point 1, 3 is going to become 1, -3. Perfect. All right. And then I have to do the other 2 transformations, and since they involve adding and subtracting, we can do them at the same time. So when it says left 2, which point or which coordinate does that impact? The x. Okay, so I'm going to say left 2, and then I'm going to say down 1, and that's going to impact the y, and I am finally impacting my horizontal asymptote. So y equals -1, down 1, down 1. Now, just like last unit when we learned about rational equations and rational functions, the number on the end of the function, this is the horizontal asymptote. So you can match that up with your chart, -1, -1, horizontal asymptote is -1, those are the same, okay? So you can put it in your chart, or you can put it when you, like, automatically find it when you get started. We already know that that's going to be -1. So we can go ahead and draw that. And then our other 2 points are -2, -2, and -1, -4. And so we always take the 2 points and we connect them, and we draw, connecting the 2 points, we go following along the asymptote, because that's what asymptotes do. So connect the 2 points and follow along the asymptote. And then after that, make sure you make your sound effect. This is important. And after that, we go whoop. No, it's not a whoosh. It's not a whoosh. It's a whoop. No, it's a whoop. Come on. It's a whoop. Oh, you guys. All right. How do you guys feel about the graph? We good? All right. Can anyone make a prediction about where the horizontal asymptote is on example 6? Prediction, where's the horizontal asymptote on number 6? It's a 4. Okay, easy peasy. Okay, and then can somebody tell me what is the parent function for number 6? What's the parent function? Yeah, y equals 4 to the x. So y equals 4 to the x, that was the parent function. That was the function with no transformations, and then it has some transformations happening to it. So sometimes they call this the base, sometimes they call this the rate of change. So I'm going to call it the rate of change just to mix things up a little bit. So what's the rate of change for this problem? Same as the base, 4. Okay, now let's go ahead and find all of our transformations. What are they? Vertical stretch of 2. What else? Okay. And what else? Okay. All right, so we're going to write our 3 pieces of information. So we have a horizontal asymptote that starts off y equals 0 before we transform it. The point 0, 1, and the point 1 base. And the base is 4, so we're going to write 1, 4. Okay. So vertical stretch of 2, does that impact the x or the y? Vertical stretch. Vertical. The y, it impacts the y. So we're going to take the y coordinate, and what are we going to do with it? Multiply it by 2. Okay. And then we've got right 2 and up 4. So Keld, what should we do now? I said right 2 and up 4. Then, well, I haven't even found the points yet, Keld. You'd know that if your eyes were up here. Yeah. Oh, that's when you got to get your cell phone out, take pictures of the screen so you can see, man. Yeah. It's almost like I know these things. All right, can somebody help Keld out because he's blind right now? Okay, so we're adding 2 to x. You said graph it. How is graph it add 2?
Well, you add 2 after you graph it, or after you add 2 and you graph it.
All right, and then we're gonna add 4. Okay. The number on the end. Plus 4. The 0 is the default in the beginning, so I did 0 default in the beginning, 0 default in the beginning. When you take your y coordinates and multiply them by 2, nothing happens. But then when you take your y coordinates and you add 4 to them, that's when you finally see a change. Hello! Oatmeal chocolate chip. Nobody wanted them. Why? Oh, we are so sorry that nobody wanted them. All right, so we are ready to graph. Any more questions? Did that make sense? We got it? Okay, so y equals 4 is our horizontal asymptote. Then we have the point 2, 6. And then, Miss Rice, can you ever get this right? 3, 12, how are we going to graph that? Don't worry, guys, we can just add lines. 3, so 9, 10, 11, 12. Oh, that's very high. It's approximately right there. Don't worry, guys, we got it. We can handle it. Are you videotaping this?
No, it's just on the thing, but I'm just watching it.
Oh, there we go. Okay. All right, so you guys, it's 21st century technology. All right, so now we connect our dots. So we're starting at the furthest dot, we're going to the closer dot, and then we follow the asymptote. And then we go the other way, and we go, whoop! Ta-da! Yes! That's the fun part. Wouldn't it be fun if the whole class together was like, whoop, 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 whoop? I think that'd be so great. You'd be like, Miss Rice does not let us sing any math songs to learn equations of things or formulas, but she does make us say foop when we graph. All right. So we have our equation graphed. Okay, how do we feel about exponential equations? Amazing. How do we feel about, what is this, the 5th or 6th time we have found these characteristics? Are we comfortable? Increasing, decreasing? Max, min? Are there, now I didn't talk about it. I kind of skipped over it. Where was max, min in the packet? Oh. So max and min is the location of the highest point of the function, the lowest point of the function. What do we know about exponential functions? You don't even have to read it because what can you tell? There's no mountaintops, there's no valleys, and so exponential functions are not going to have maximums and minimums. No mountaintops, no valleys. Does that make sense? So this is another function we don't really find those for. What about continuity? Yeah, if you trace this with your finger, what's going to happen? You'll be able to trace it with your finger, and so these are always continuous. So these are kind of boring for those questions about max, min, and continuity. Okay, let me go ahead and get the practice assignment for you, and then we can work on that for